The next result I want to prove is result E here. And the reason is this one's a little different from the other ones. All of the other cases here, we're just showing some things are equal to each other. And so you can prove this by just computing one side of the equation, then the other side of the equation, and then making sure that they're equal. Okay? E is a little bit different. We're not just showing two things are equal. We want to show that if I take the dot product of a vector with itself, it's going to be greater than or equal to 0, and that it equals 0 if and only if the vector is 0. So this is actually almost two separate statements. We're going to need to first show this, that a dot product of a vector with itself is 0, and then separately show this, that the dot product of a vector with itself is 0 if and only if the vector is 0. Okay, so let's start with this one. So this is part E, proof. We want to start with the definition. So first I'm going to take the definition of a vector as before. So let's let U equal, we know it's an n-dimensional vector, so it has n components. So let's say it has components u1, u2, all the way to un. And what I want to do is I want to use the definition. So I want to show that the dot product of a vector with itself is greater than or equal to 0. So let's start by actually computing what the dot product of a vector with itself is. Observe that if I take the dot product of U with itself, that's going to be the dot product of U1, U2, all the way to UN. And I take the dot product of that with U1, U2, all the way to UN. And so I am going to multiply corresponding components. So first component of the first vector times first component of the second vector. So U1 times U1 plus second component of the first vector times second component of the second vector. And I keep on doing that until I multiply the last component of the first vector with the last component of the second vector. Okay, and I could tidy this up a little bit more since U1 and U1 is the same number. U2 and U2 is the same number, and so on. U1 times U1 is U1 squared. U2 times U2 is U2 squared. And UN times UN is UN squared. All of the components get squared because the corresponding components in each step are equal, since the vectors are equal. Okay? Now, once we write out what U dot U is, once we use the definition of the dot product to write out what U dot U is, this first step becomes pretty easy to see, because what do we see? We see that we're adding a bunch of squared numbers. And what do we know about a squared number? A squared number is always going to be non-negative. It's going to be greater than or equal to 0. So recall that ui squared, where I is some subscript, it could be 1 or 2 or any of the subscripts. Recall that ui squared is not going to be negative. It's going to be greater than or equal to 0. Now, it could be 0 if ui is 0, but most of the time it's going to be positive, right? You square a number that's not 0, you get a positive. And then I'm just going to say for all I, meaning for any subscript I that I want here. Okay. since u dot u equals u1 squared plus u2 squared plus dot 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 un squared is the sum of non-negative numbers it must be that u dot u is also non-negative. Okay, that proves this first statement here. Okay, now it looks complicated. Note that all I did was use the definitions. Oh, what's a vector? It's n numbers, n component numbers. Okay, if I take a dot product of a vector with itself, what do I get? Oh, I'll just get the first component times the first component, the second component times the second component, all added together. And since the components are the same, I get to square them. And then once I got here, seeing why this was positive is easy. I'm just adding a bunch of non-negative numbers. And so the result is also non-negative. Okay? So a lot of times it's not obvious here why that's true. But if you apply the definition, you can get to a point where it is often obvious. Okay, so I'll repeat this many times in this class. When you're working on a proof, and if you're not sure where to start, go back to the definition. What does it mean to be a vector? What does it mean to take a dot product? See what happens when you apply the definition. Okay, so this first statement is proved. Now let's go to the second statement here. This one's a little trickier because we have an if and only if. We haven't seen this before. An if and only if means we actually kind of have to do two proofs, one for each direction. Okay, if I see A if and only if B, that means two things. That means if A, then B, and if B, then A. And I have to prove that both of these are true because they're not always. So consider an example. If K is an even number, then it is divisible by a prime. Okay, so in this case, this might be my A. If K is an even number, so that's my A, then it is divisible by a prime. That's my B. Use a different color. So if A, then B. And we can see that's true, right? Because if K is an even number, well, every even number is divisible by 2. That's what it means to be an even number. And 2 is a prime. Okay, so every even number is divisible by 2. Every even number is divisible by a prime. Great. That checks out. But if I think about it the other way, if K is divisible by a prime, then it is an even number. So here, this would be statement A. This would be statement B. Okay, but is this true? If K is divisible by a prime, then is it an even number? Well, obviously not. Let me think of a better example. 9. 9 is divisible by a prime. 9 is divisible by 3, but 9 is not an even number. So this statement is false. Okay? When we see if and only if, that means we need this to be true and also this to be true. And so usually we have to prove both directions. Okay. Okay. So I'm going to start with this direction first. That is, I'm going to assume if u equals 0 and then show that then u dot u equals 0. Okay, so we'll sometimes use arrows to show the direction. Now, assume vector u is the 0 vector. What does it mean to be the 0 vector? It means it is the vector with all 0 components. So notice again, I'm going to the definition. What does it mean to be the 0 vector? What's the definition of being the 0 vector? It means it's a vector where every component in the vector is 0. And here we have n components. Notice I don't use u 0 sub 1, 0 sub 2, 0 sub n. We only use subscripts for variables, not numbers. Okay? So up here, I could do u sub 1, u sub 2, u sub n, and then it's very clear that I have n components. Here, we do not use subscripts for numbers. 0 sub 1, 0 sub 2, 0 sub n, that just looks ugly. Okay, so if we need to emphasize how many components we have, we could say it like I do right here. Okay, so now I'm going to prove that u dot u equals 0 by just doing the definition, doing the calculation. Okay, so if I just apply the definition of a dot product, I'm going to multiply first component times first component plus second component times second component. I'm going to do that for all the components. In this case, all the components are 0. If I multiply a bunch of zeros together and then add all those zeros together, I just get 0. And that's what I needed to prove for that first step. Okay, I proved this direction. If u is 0, then u dot u is 0. I've still got one direction to prove. If u dot u is 0, then u is 0. Okay, so now I'm going to assume u dot u is 0. So now we look in this direction. So finally, assume u dot u is 0. So what I'm going to do is I'm going to use the work I've already done. I know u dot u, if u is expressed in this way, then I can write u in this way. Notice, by the way, that in each section, we're kind of defining u differently. So in this first section, I defined u very generally. Once I got to this section, I made an assumption that u was 0. So I defined u as being the 0 vector. Okay. Now I'm again going this direction, and I don't know what u is, but I know the dot product of u with itself is 0. So if u is u1, u2, all the way to un, then 0, which is equal to u dot u by my assumption, must be equal to u1 squared plus u2 squared all the way to un squared. And I already did that up here, right? I'm defining u the same way as I did up here. So u dot u must equal to this. Okay? But what do we know about the u's here? Well, I'm adding a bunch of non-negative numbers. Remember that? But ui squared must be greater than or equal to 0 for each I, because they're squared. The only way I can add non-negative numbers and get 0 is if each number is 0. And that's exactly what I'm doing here, right? I'm adding a bunch of non-negative numbers because these are squared, they're not negative, and I'm getting 0. The only way I could add a bunch of stuff that's not negative and get 0 is if each number is 0. If any one of these numbers weren't 0, there's no way to subtract it off, right? Because I have a bunch of non-negative numbers. I can't subtract it off. So ui must be equal to 0 for each I. ui squared must be equal to 0 for each I. Well, the only number that when I square it I get 0 is 0. Now remember, when I say for each I mean I equals 1, I equals 2, I equals n, these subscripts. Okay? So for each one of these subscripts, it must be equal to 0. u1 must be 0. u2 must be 0. All the way to un, it must be 0. Therefore, vector u, which is components u1, u2, all the way to un, well, u1 must be 0. u2 must be 0. All these ui's must be 0. All these u's with subscripts must be 0. And a vector of all zeros is the 0 vector. And that's what I wanted to show going in this direction. I wanted to show that if the dot product of a vector with itself is 0, then the vector must be 0. And I've done that. I started with assuming that the dot product of a vector with itself is 0, and now I've shown, oh, yeah, the vector must be 0. Okay, so this is a more complicated proof. Obviously, there's a lot of steps. A large part of that is because there was multiple claims in the same line, right? It wasn't just this claim, and it wasn't just this direction or this direction. There was 3 things going on in one line. We had to prove all of them, okay? So you have to be very careful that you prove every claim in a claim, okay?